Hi everyone, it's great to see you here today. So I'm Youssef Ben Dhieb. I work as a high performance computing lead at Dhieb. Also, I'm a Google developer expert in machine learning. And today I'm going to talk about computer vision in deep learning. So first, what's computer vision? So computer vision is a scientific multidisciplinary field. Its goal is to make computers understand images and videos, and it seeks to automate tasks that the human visual system can do. So how basically computers see images. So this is, for example, a colored image of a cat, an RGB image. So each pixels has three values, one for the amount of the red color, one for the amount of green color, and one for the amount of blue color. And for example, for this task here, we are trying to classify an image. So the first task is the image classification. So we have an image and we try to classify it if it's a cat or a dog. Another types of tasks in computer vision are, for example, object detection, which is different from image classification. We have to detect all the objects in a given image. Another one also is semantic segmentation. For this task, the output is an image with the same size of the original image, but where each pixel has a value, and this value is the class the class that this pixel belongs to. For example, for this class in blue here, it's a vehicle. For this class in green here, it's the tree. So it's, for example, for this pixel, each pixel has a value of 5, for example, if the class is 5 for the vehicle. Another task would be the instance segmentation. It's the same as the semantic segmentation, but the difference is that we can differentiate between objects. So in here, as you see, you cannot find how many trees you have in this picture, but in instance segmentation, you detect each object apart. Another type is the object tracking. We use it in videos. So we try to track a moving object in a video. So how could we use deep learning for these tasks? So first of all, we have to understand neural networks. So neural networks were inspired by the biological neurons, by our brains. So our brains contains millions of these neurons, and in biological neurons, it has some inputs here. We call them dendrites, and it outputs. It has also some outputs. We call them the axon terminals. So in artificial neurons, we are doing basically the same thing. So this is a single artificial neural. So here we have our inputs, for example, for the pixels of the image, and it gives us an output which is the x1 here, the input, multiplied by the weight, and we do that for each input. Then we sum them up and add the bias. Okay. So our work in artificial neurons, so our objective is to optimize these values, to find the best values for W1, W2, and B, which are W's here are the weights, and B is the bias. So also we add another function to artificial neurons. So after multiplying the input by the weights and add the bias, we apply a function, an activation function, we call it. It can be a sigmoid function, a tanh function, or a ReLU function, for example. So for here, we use the sigmoid function. And we use, for example, the sigmoid function if we want the output to be between 0 and 1. Okay, we want to classify, for a classification problem, we want to get a probability if it's in this class or not. So we get a probability between 0 and 1. So a simple classification problem. So here we have the first points here that belong to the first category. And we have these points here in the negative side, which belong to the second category. So how can we use the neural network to classify these points? So if we choose a neuron, for example, so as we said, our objective is to find the W's, the weights, and the bias. So if we choose a neuron from this side, for example, so the inputs will be, for example, for this neuron here, it will be 0.5 and 0.5. And at the end, we want the network to output 1 for the first class. So we should do an optimization over all the points here to find the best values of omega 1, omega 2, and B. And the same for this class here. If the inputs are, for example, minus 0.5 and minus 0.5, and the output should be 0, what are the best weights we can find here? So just a demonstration for a single neuron. Okay, so in this playground here developed by the Google team, you can try with different architectures of neural networks. So for example, we will choose a simple classification dataset. Yeah, for this one, for example, like the one I showed. So I will add a neuron here. And when we train the program, it will detect each, it will classify the points, okay, into classes. So you can play a bit with the weights here when you choose the weight. For example, for the W1, for the first weight, as I change here the value of the weight, you can see the output of the neuron, okay? And for this weight also. So for neural networks, what we are doing basically is that we are looking for the best value of these weights. Okay, so they start randomly, like that, for example. Then we train the network to find the W1, W2, and B. So here is also the bias. So you can see the effect of the B, the bias there, how it affects the output of the network. Okay. So for a more complex case, like this one, this can never be done by a single artificial neuron. So for this one also we have to change the architecture, since we cannot get a line that differentiates between the two classes. So we have to add more layers or add more neurons. So we go back to the playground again and choose this type of data set. So if we try to find the best architecture here using one neuron, as you can see, it cannot find the best solution for that. So here we have to add a few more neurons. Let's add 2 neurons in here and add another 2 neurons after them. So as you can see, it couldn't classify them correctly. So let's choose a sigmoid activation function. So I advise you to play a little bit with this playground. Let's set the regularization. Okay. Okay. So when you hover over each neuron, you can see the output of that neuron. Let me change this. And change this to ReLU. Yeah. So just change the activation function. As you can see here, the network. So assigned all this space here and here for the first class, and all this space here for the second class. Okay. So what if we have multiple classes, not only one class? So in that case, like this one, we should have in the output, for example, we have 3 classes, so we should have 3 neurons at the end. And here, when we will use, for example, the tan-h function, we will get an output between -1 and 1. So we will get, for example, for a specific point, we will get 0.8 here, -0.7 here, and 0.5 here. So the problem in here is that these are not probabilities. So what should we do to have them as probabilities? We use the softmax function. So what the softmax function is doing, it's like a standard normalization, but it uses the exponential function. And we do that because we have negative values here. So for each one of these outputs, we take the exponential of the output, then divide it by the exponential of the other outputs. So we will get a probability of 1 at the end, okay? So always in the classification problem, we use the softmax function. And after that, how could we compare the output of the network with the true labels that we have? So for that, we use one-hot encoding, which is, for example, if we have a class 1 as a true label, so we create a vector having as length the number of classes. So here we have a vector of 3. So the first class, we will assign 1 to the first element of the vector and 0 for the others. For the second class, we will assign 1 for the second element of the vector, and so on. So after that, we did the one-hot encoding. So how could we train the neural network for that? So for that, we will use a loss function. We create a cost function, or we call it also as a loss function. So the loss for the multi-classification task, the loss we use is the multi-class cross-entropy loss. Okay, so we multiply the white rule, the true label, by the log of the prediction, and we sum them together and we add the minus sign. So for example, for here we had 0.8 minus 0.7, 0.5 here. We compute the softmax so that we can have probabilities. So as you can see here, the one that has the biggest probability is 0.51. And for the true label, we have this class as a true. So we multiply 1 by log of 0.51, and we add the minus sign, then add these others. But since these others have 0 as a true label, so we will get them out from the equation. And at the end, we will get the value for the loss function. So after that, we do the backpropagation. I'm not going to dive into this since it's very mathematical. So now, after using these neural networks, we will talk about other architectures for image processing. So because the other ones are for very simple classification problems. So for image classification, how could we do? So this is the MNIST dataset. We have a lot of images of handwritten digits from 0 to 9. So we have 10 classes. And for each images, its size is 28 by 28, 28 by 28 pixels. And each pixel here has a value between 0 and 255 as the level of gray. So for example, the white pixels here have a value of 0, and the black pixels have a value of 255. So what we'll do basically is that we are going to flatten the image. We have a 28 by 28 image. So we'll flatten it in one vector. It will have the length of 784 pixels. Okay. Then what we do, we'll add 10 neurons, okay, for each class. Then we compute the softmax and compute the loss and do the backpropagation. So in a mathematical way, how could we do that? So since we have 784 pixels for each image, and we have here 100 images, so we multiply it by another matrix containing the weights and the biases, no, the weights. Then we add the biases here. So we multiply the first image, for example, for here it's the number 8. So we multiply these pixels by these weights here. Okay, so each input will have a weight. Then we add the bias, and after that we do the softmax function. Okay, so all the equations for this network will be the softmax of the inputs times the weights plus the biases. And in TensorFlow, we could do that in just one line of code using tf.nn.softmax and tf.matmul. Matmul is a matrix multiplication of the inputs by the weights, then adding the biases. Then we compute the cross entropy loss. For example, for the digit number 6, we have the one hot encoded label, all zeros. Only the sixth element is the seventh element is 1, and here we have the probabilities outputted from the softmax. So we'll use these two to compute the loss function. So for a very simple neural network like this one, we have only 10 neurons. And on the MNIST dataset, we are able to have an accuracy of 92%. If we train this model, we get a 92%. We'll do that in a while. Okay, you will implement it by yourselves. So in TensorFlow, in order to implement that, we will use the high-level API Keras. It's very easy to use. So first, we have to import TensorFlow in Python. Import TensorFlow as TF. Then we have to load the MNIST dataset. So it's implemented in Keras. Then we have to split in the X train, Y train, and X test, Y test. So the X is the input and Y is the output. And we have to divide them into a train test and test set. So the train set is used for training the neural network. Then after it learns from them, we will use the test set to evaluate it on images that it didn't see, it has never seen, in order to have a real meaning of the training. And after that, also, we will divide the inputs by 255, since we say that the pixels have a value of between 0 and 255. So we want to normalize them and make them between 0 and 1. After that, we have to define the model. So the model we just talked about is a sequential model, but has only 2 layers. So the first one is tf.keras.layers that flatten. This one we use it to flatten the images. We add the input here, which is 28 by 28 for the images. And the second layer is the dense layer, or we call it also fully connected layer. It has 10 neurons, and the activation function is tf.nn.softmax. So this is the whole model. And after that, when we use model.summary, we will get a summary of our model, how many total parameters we have, and how many trainable parameters. So the W's, the weights, and the biases, these are the trainable parameters. After that, we have to compile the model. So we use model.compile. Okay, we choose the optimizer. Here we are using the stochastic gradient descent optimizer. We choose the learning rate. We'll talk about that later. And for the loss, we use the cross entropy loss. And for the metrics, we use the accuracy metrics. Okay. And in order to train the model, we just use model.fit. We give it the inputs, x equals x train, y receives y train, the true labels, and the number of images to train at once, which is 100 image, and the number of epochs. This is the number of times to train on the whole dataset, to train the model on the whole dataset. And we give it also the validation data to give us the metrics on the validation. So this is basically the whole code for training this model. So now that we got 92% on classifying the images of the MNIST dataset, let's try a bigger model where we use 5 layers. So like this one. So for the first layer, we will use 200 neurons. For the second 100 neurons, 60, 30, and then in the output, we should always have 10, since we have 10 classes. And we will use softmax also. And for all these neurons here, we will use the sigmoid function. So the only difference in the code for using these 5 layers is just to add the dense layers here. So we add 4 hidden layers here. So the dense layer we added using tf.chars.layers.dense, and we put the number of the neurons we want in our layer. The activation then is a sigmoid, tf.nn.sigmoid, and we can name it each layer. So at the end also we have the dense layer, which has 10 neurons for the 10 classes, and the activation will be the softmax function. So when training the model, you will see that it doesn't evolve very fast. So for that we use the ReLU function. So the ReLU function, what it does basically is that at the output of the neuron, if we have a negative value, it will give us a 0. And if we have a positive value, it will give us that value. So for this part, it will be f of x equals to x. And for this part, it will be 0. And the ReLU function is used in TensorFlow as tf.nn.ReLU. So these are the results from the sigmoid activation functions. When we use the ReLU, we will find that it will progress very fast. It will evolve very fast and train very fast. So the problem after that, we will find some spikes in here. And this is due to the learning rate. So we have to reduce the learning rate after some iterations. So at the beginning, the learning rate was 0.003. Then we will drop it exponentially to 0.001. So as you can see, this is the difference for 0.03. And this is using learning rate decay, when we decay the learning rate. So using this model with just 5 layers of neural networks, of neurons, we are able to get 95% accuracy on the MNIST dataset on classifying the digits images. So the problem here is on the test data. So the blue one here is for the training data, our loss. So the loss is going okay, it's reducing for the training, but for the test loss, after some time, it becomes to increase, and we call that overfitting. So what the neural network here is doing is that it learns the training images, and it's not able anymore to generalize on images that it hasn't seen before. So for that, we will add the dropout. So the principle of the dropout is that we drop some neurons, okay, when training. So when the information goes to here, we will drop these values, and we will not train these neurons, because what the model is doing when we do not use dropout, it will store the images in these neurons and output the images that it has already seen, and cannot generalize to newer images. So for example here, the value of the dropout is 0.5. So we drop randomly 50% of the neurons. And we can change this value, depends on your network, the network you are using. You can put it 0.2, 0.3, depends. It's the ratio of the discarded neurons in your network. So if it's 0.2, for example, we will discard only 20% of the neurons. So in order to use the dropout, we just add an activation, another layer after the fully connected layer. So we will use also tf.chars.layers, and we just write dropout, and we put the dropout rate here. So using dropout, as you can see here, we'll reduce the loss. So here without the dropout, and we see here with the dropout. Also, this is using the learning rate decay. So if you are also still overfitting, if you added the dropout and you still have the overfitting, so what you should do here is that you should understand that you have maybe too many neurons. You should reduce the number of layers or the number of neurons in each layer. or you have not enough data. So, for example, for the MNIST data set, I think it's 8,000 images or something like that. So you should add more data. But in our case here, we do not have too many neurons, and we have enough data for the MNIST data set. So the problem is that we have a bad network. So a newer architecture. Here is the convolutional neural network. So why we use the convolutional here? Yeah. Okay. A bad network means that you have a bad architecture. So what we were doing at first, we are flattening the images and then adding fully convolutional layers. So what should we do for now? We should change the type of layers. So we will use convolutional layers. And why we use convolutions? We want the original image to stay to have the same size, okay, and the same length and width, okay, because it contains spatial information. So we are not going to flatten it anymore. So we will use convolutions instead of fully connected layers. So we will use some filters here of 4 by 4. So for the first neuron, then another filter for the second neuron, and another one. So we do that over the width of the image, and we do also the same over the length of the image. So we'll get a layer of neural networks here, which has the same size of the original image. Then after that, we will create other layers the same way, but we will use we'll have as output smaller size and width, until at the end we will get a fully connected layer and 10 outputs. So we can also we can change the size of this layer using the padding in Stride. So the padding is the pixels outside the image. So we can use the padding here to have the same size here. So we add some pixels at the edges, and we give them as a value of 0, for example. And the Stride is the step that we use for this kernel here. The step here, it goes by, for example, by 1 pixel or by 2 pixels. So we call it Stride. So if, for example, if we use, sorry? Oh. Okay. So if we use a Stride of 2, for example, we will get half the size of the original image here. So let's build a neural network using convolutional neural networks. So here, when we will use a filter of size 5 by 5 and a Stride of 1 and padding of 4. So we will get here the same shape in here. Then we will get half the shape we had at the beginning, then half of it again. And after that, we will use a fully connected layer with 200 units. And at the end, we will use a fully connected layer of 10 units as the number of classes. So in order to create this model, we'll use also tf.keras. So we will have just to change the type of layer here. Instead of dense, we will use conv2d. And the size of the channels, the output channels in here. For the first rail, we'll choose 6. And the size of the kernel, it will be 6 pixels by 6 pixels. And the padding here is the same. So we are adding some pixels at the edges. The strides equal to 1, and the activation is ReLU. So we'll add 3 convolution layer, then flatten the last one, and use the fully connected layer or dense layer with 200 units. Then at the end, we will use the dense layer with 10 units as the output. So using this convolutional network, we are able to get 98 by 9% as accuracy in the MNIST dataset. So also here we will find that we are facing overfitting. So what should we do again? We should add the dropout. Yeah, We should add the dropout here. We never use the dropout in the convolution layer. We just use it in the dense layers at the end. And using that, we are able to get a 99.3% as accuracy in the MNIST dataset. Okay, this is the effect of the dropout on the convolutional layer. Okay, so I don't know if you you brought your laptops. No. Okay, for the presentation link, if you want to have the presentation, so you just write a bit.ly, then AAIS presentation. And for the notebook, if you want to practice, so you use this link, bit.ly AAIS notebook. Okay, so this is the notebook. It's in the Google Colab. So in Google Colab, Google will provide a free GPU. You can use it for training the network. And it will provide a notebook interface where you can build Python programs using TensorFlow. It's pre-installed in here. So I will go roughly over the notebook here. So you just run the first cell here to install TensorFlow and other dependencies. As you can see here, we will install TensorFlow GPU 2.0. Okay. So you just have to follow this notebook step by step. So it's basically based on TensorFlow without PhD by Martin Gardner. So for the first cell, you will install the dependencies. So usually we use these notebooks on Google Colab because it can install dependencies and all of these things faster than you install them locally. And also you have a free GPU that you can work on, because the training, it will take a lot of time on CPU unless you have a GPU in your computer, or you can use this notebook here. So we have just to wait for the installation of TensorFlow. By the way, do you have any questions on the... Yeah, no? Thank you.